If you were to look for an alien on Earth, you wouldn't look to the stars. You would look to the seafloor. To understand the octopus, we must first accept a humbling reality. Our definition of life is heavily biased toward our own blueprint. For hundreds of millions of years, evolution has followed a predictable, centralized script. Most complex animals, from insects to mammals, operate on a hierarchical command structure. A central brain processes data, sends a signal down a spinal cord, and the limbs obey. This is the top-down architecture of terrestrial life. But the octopus has discarded the script entirely. They are what biologists call an evolutionary outlier, a radical departure from the standard trajectory of animal intelligence. While our ancestors were busy refining the vertebrate model of a protected skull and a central nervous system, the ancestors of the cephalopod were moving in a completely different direction. They didn't just evolve, they diverged. Consider their anatomy. The octopus lacks a skeleton. In a world where strength is typically derived from bone and structure, the octopus has chosen radical fluidity. This lack of rigid architecture is not a weakness, but a profound evolutionary gamble. It allows for a degree of morphological plasticity that no other creature possesses. They can compress their entire existence through a hole the size of a coin, turning their very bodies into a tool of deception and escape. But the true anomaly lies in their genetic blueprint. Recent genomic sequencing has revealed something staggering. The octopus genome is a playground of complexity. They possess a massive number of genes dedicated to RNA editing. In most animals, the DNA provides a fixed set of instructions. If you need to adapt to a temperature change or a new predator, you must wait generations for natural selection to hardwire that change into your offspring. The octopus, however, performs a sort of biological, real-time editing. They can manipulate their own RNA to change how their proteins function, allowing them to adapt to environmental shifts within a single lifetime. It is as if they have found a way to rewrite their own software while the computer is still running. Furthermore, their neurological layout defies the very concept of the individual. In a human, the brain is the seat of the self. In an octopus, the self is distributed. Roughly 2/3 of their neurons are not located in the head, but are tucked away in the arms. Each limb possesses a degree of autonomy, capable of sensing, tasting, and reacting to the world without waiting for permission from the central brain. This is not just a nervous system. It is a decentralized network, a biological internet of living sensors. They are an experiment in what intelligence looks like when it is untethered from the vertebrate tradition. They have solved the problems of survival, camouflage, and predation using a toolkit that looks nothing like our own. When we study the octopus, we aren't just looking at a different species. We are looking at a different way to be alive. They are a reminder that evolution does not have a single goal, and that greatness does not always require a spine. But if we are to truly grasp the magnitude of this divergence, we have to confront a more uncomfortable question. What if our very definition of intelligence is broken? For centuries, the human intellect has acted as the yardstick for all sentient life. We have measured consciousness through a narrow lens, the ability to use language, the capacity for logical reasoning, and the presence of a centralized, commanding ego. We assume that to be smart is to possess a singular, internal I that sits behind the eyes, pulling the levers of the body. We look for a reflection of ourselves in the animal kingdom. The octopus, however, is a mirror that reflects nothing of our own experience. It represents a non-human intelligence, a cognitive architecture that does not just function differently, but exists on an entirely different philosophical plane. In the vertebrate model, intelligence is a dictatorship. The brain is the sovereign and the body is the subject. But the octopus suggests a model of intelligence that is more akin to a democracy or perhaps a sophisticated cloud network. When an octopus reaches out to explore a crevice, its arms are not merely executing commands, They are making local decisions. They are weighing textures, tasting chemical signatures, and calculating trajectories independently. This brings us to a concept that challenges our notion of the self, the idea of a distributed consciousness. In a human, if you lose a limb, you lose a tool. In an octopus, if a limb is lost, the mind that inhabited that limb is partially severed. The intelligence is not housed in a single vault, it is woven into the very fabric of their flesh. This raises a profound scientific mystery. Where does the mind of an octopus actually reside? Is it in the central brain, or is the octopus a collective of 8 semi-autonomous intelligences working in a silent, liquid harmony? This is not merely a biological curiosity, it is a cognitive revolution. We are seeing a form of embodied intelligence that we are only beginning to model in our own technology. When we build artificial neural networks, we are trying to mimic the very decentralized, parallel processing that the octopus has mastered for millions of years. To study the octopus is to realize that we have been looking for intelligence in all the wrong places. We have been looking for a pilot in a cockpit, when the octopus has turned the entire aircraft into the pilot. They prove that sentience does not require a central command post, and that complex thought does not require a human-like ego. They invite us to step outside our anthropocentric bubble and consider a universe where mind can emerge from 1,000 different configurations. They are the ultimate proof that there is no correct way to think. There is only the infinite variety of how life finds a way to perceive the dark. As we move deeper into their world, we must prepare to abandon our biases and accept that we are not the only way to be wise. But before we can dissect the mechanics of their decentralized mind, we must first confront the impossibility of their presence. Imagine you are drifting through the twilight zone of a coral reef. The landscape is a static tableau of jagged limestone, swaying anemones, and rhythmic shadows. You feel certain of what you see, and then, in a heartbeat, the landscape breathes. A patch of sand ripples, a texture shifts, and a shape that was indistinguishable from a rock suddenly flows, pulses, and vanishes. This is the first, and perhaps most jarring, encounter with the octopus, the realization that your eyes have been lying to you. To witness an octopus in motion is to witness a masterclass in sensory wizardry. They do not merely hide, they rewrite the visual reality of their surroundings. This is achieved through a biological marvel known as chromatophores, microscopic, pigment-filled sacs packed into the skin. By contracting or expanding these sacs via tiny muscles, the octopus can deploy a kaleidoscopic array of colors in milliseconds. But the trick is far more sophisticated than simple pigment change. Beyond color, they possess iridophores and leucophores. These are reflective cells that manipulate light itself, creating iridescent blues, greens, and silvers that mimic the way sunlight filters through the water column. They can replicate the exact texture of a coarse sponge or the smooth, calcified surface of a shell using specialized skin protrusions called papillae. These papillae can be raised or lowered instantly, transforming a soft, streamlined body into a jagged, three-dimensional mimic. Yet, the true genius of this camouflage lies in the speed of the processing. This isn't a slow, conscious decision like a person choosing a disguise. It is an instantaneous, near-reflexive reaction to the environment. Recent research suggests that this visual transformation is driven by a high-speed loop between the eyes and the skin. The octopus's eyes are incredibly advanced, capable of detecting polarization, a nuance of light that most humans cannot perceive. They see the world in a high-contrast, hyper-detailed spectrum, allowing them to perceive the subtle shimmer of a predator's movement or the specific light pattern of a hiding spot. This visual data is then translated into a command that travels through the nervous system, triggering the skin to reorganize its very appearance. But here is the most unsettling part. The camouflage isn't just about looking like something else, it's about being nothing at all. By matching the light, the the texture and the color of the seafloor, the octopus achieves a state of optical invisibility. They exploit the blind spots of evolution. They use their sensory mastery to slip through the cracks of the predator's perception, becoming a ghost in the machine of the ocean. When we first observe this, we aren't just seeing a survival mechanism. We are seeing the first hint of a profound cognitive depth. This level of real-time environmental integration requires more than just instinct. It requires a continuous, high-speed synthesis of light, texture, and spatial awareness. It is the first clue that the octopus isn't just living in its environment. It is actively, intelligently, and invisibly reshaping it. To understand how they achieve this magic, we must look past the skin and dive into the very architecture of their being. To understand how a creature can rewrite its own reality, we have to ask a deeper question. How did such a radical design come to exist in the first place? To find the answer, we have to travel back through the deep time of our oceans, long before the first dinosaur ever walked the earth. The story of the octopus is not one of steady, predictable progress. It is a story of evolutionary divergence so profound that it feels less like a branch on the tree of life and more like a separate forest entirely. The lineage of the cephalopod, meaning head-foot, began over 500 million years ago. In the Cambrian explosion, the ancestors of these creatures were nothing like the geniuses we see today. They were likely simple, soft-bodied organisms, perhaps resembling modern worms or primitive mollusks, drifting through a primordial sea. For millions of years, the molluscan blueprint remained relatively conservative. We see this in their cousins. The clams, which chose the path of stability, anchoring themselves to the seafloor, and the snails, which opted for the heavy protection of a shell. But the cephalopod lineage took a different, more dangerous gamble. They abandoned the fortress. During the Paleozoic era, a pivotal split occurred. While most mollusks doubled down on calcium carbonate armor, the ancestors of the octopus began to shed it. They traded the safety of a heavy shell for the freedom of movement. This was a high-stakes evolutionary pivot. By losing their external protection, they became vulnerable to almost everything in the ocean. To survive this nakedness, they couldn't rely on armor. They had to rely on something else: speed, sophisticated sensory systems, and, eventually, intelligence. As we move into the Mesozoic era, we see the emergence of the colloid cephalopods, the group that includes octopuses, squid, and cuttlefish. This is where the blueprint truly begins to warp into something alien. While their relatives, the nautilus, retained a chambered shell to control buoyancy, the colloids underwent a process of internalizing or completely eliminating their shells. This deshelling opened a door to a new way of being. Without a rigid casing, their bodies became fluid, capable of squeezing through gaps no larger than their own beak. But the most striking aspect of this lineage is the arms race of the nervous system. As they moved from the slow, armored life of a snail to the high-velocity life of a hunter, their metabolic demands skyrocketed. To process the massive influx of data from a world without a shell to hide in, their nervous systems had to undergo a massive expansion. We see a fascinating phenomenon here: convergent evolution. The octopus developed complex eyes that function remarkably similar to our own, yet they evolved entirely independently from the vertebrate lineage. They arrived at the same solution to the problem of sight, using a completely different biological toolkit. This is the cephalopod blueprint, a history defined by the courage to be vulnerable. They are the descendants of survivors who realized that in a world of predators, the ultimate defense isn't a wall of bone or shell. It is the ability to outthink, outmaneuver, and outsmart the world around them. They didn't just evolve to live in the ocean, they evolved to master it. But as we stand before these masters of maneuverability, we encounter a profound intellectual roadblock. We look at them and we say, That is smart. We see an octopus unscrewing a jar or navigating a complex labyrinth or using a coconut shell as a mobile fortress, and our instinct is to categorize it. We want to put them on a scale, next to the chimpanzee, the dolphin, or the crow. But here is the problem. Our very definition of intelligence is deeply, perhaps even dangerously, biased. For centuries, biology has operated under a vertebrate standard. When we design tests for intelligence, we design them for creatures that look, act, and think like us. We look for centralized processing, a single command and control hub located in a skull, managing a body through a unified stream of consciousness. We equate smart with the ability to use tools, to solve puzzles, and to communicate through shared symbols. We have built a mental cage of what intelligence should look like, and we have mistakenly assumed that if a creature doesn't fit the bars, it isn't thinking. The octopus shatters that cage. When we try to measure their cognitive depth, we run into the intelligence gap, the chasm between how we perceive mind and how the octopus actually experiences it. In a human, intelligence is a hierarchy. There is a king and there are subjects, but in an octopus, the hierarchy is dissolved. Consider the sheer neurological strangeness of their existence. Roughly 2/3 of an octopus's neurons are not located in the central brain at all. They are distributed throughout the arms. This means that when an octopus reaches into a crevice, the arm isn't just receiving orders from a central commander. It is making its own decisions. It is sensing, tasting, and reacting with a level of local autonomy that we can barely conceive. It is a distributed intelligence, a swarm of semi-autonomous minds working in concert under a singular, soft-bodied umbrella. This challenges our most fundamental philosophical assumption, that there must be a self at the center of the experience. If the arms can think independently, where does the I actually reside? Is the octopus a single individual, or is it a collection of intelligent parts? Furthermore, we struggle with the language of mind. We define intelligence through social learning, the ability to pass knowledge from parent to offspring. But the octopus is a solitary ghost. They live, they learn, and they die in total isolation, never passing their hard-won wisdom to a new generation. This breaks our traditional metric of cultural intelligence. In our eyes, a genius who cannot teach is a biological dead end. But in the ocean, this ephemeral genius has thrived for millions of years. We are trying to measure a multidimensional, decentralized, fluid intelligence using a one-dimensional, centralized, rigid ruler. To truly understand the octopus, we cannot simply ask if they are as smart as us. We have to ask a much more unsettling question. What if intelligence doesn't need a center? What if the most brilliant mind on Earth is one that doesn't even have a self in the way we understand it? If we cannot even agree on what intelligence is, how can we hope to map its most alien expression? We are standing at the edge of a cognitive frontier, peering into a darkness that is not merely a lack of light, but a lack of understanding. To embark on this journey is to accept that everything we thought we knew about the architecture of thought is incomplete. We are not just studying a different species, we are studying a different way of being. As we move forward, we must prepare ourselves to abandon the comfort of the familiar. We will dive deep into the microscopic architecture of the cephalopod nervous system, where we will find something far more complex than a simple brain. We will explore the concept of RNA editing, a biological phenomenon where the octopus can rewrite its own genetic instructions on the fly to adapt to temperature changes. This isn't just evolution over millennia, it is real-time, molecular problem-solving. It is a level of biological plasticity that makes our own rigid genetic code look like a static blueprint. We will witness the tactical brilliance of the hunter and the architect, observing how these creatures manipulate their environment with a precision that rivals our most advanced robotics. We will see how they turn their very skin into a high-definition screen, utilizing millions of specialized cells called chromatophores, iridophores, and leucophores to communicate and vanish in the blink of an eye. But we will also see the shadow side of this brilliance, the biological tragedy of a mind that burns too brightly and too briefly. This documentary is not a simple catalog of clever tricks. It is an investigation into a profound biological paradox. We will ask why a creature with such staggering cognitive potential is programmed for such a lonely, fleeting existence. Why does evolution grant them the tools of a god, only to deny them the ability to pass those tools to their children? We will move from the how of their biology to the why of their behavior, and finally, to the what if of their existence. What if the octopus is not an evolutionary accident, but a proof of concept? A proof that consciousness is not a prerequisite for complexity, and that a mind does not need a soul, or a spine, or even a central command to master the world. The path ahead is a descent into the profound. We will navigate through the decentralized neurons of the limb, the sophisticated camouflage of the skin, and the heartbreaking isolation of the solitary genius. We are moving past the vertebrate standard and into a realm where the rules of thought are rewritten. Prepare to leave the shore of human logic behind. We are going beneath the surface to meet a mind that is not just different, but fundamentally, beautifully, and terrifyingly other. The voyage into the great unknown begins now. To understand this alien mind, we must first locate its anchor. In the vertebrate world, the world of humans, dogs, and even fish, the brain is a supreme dictator. It is a singular, centralized command center housed within a protective bony vault, issuing orders that the rest of the body must obey. But as we descend into the anatomy of the octopus, we find that the traditional hierarchy of command is shattered. At the very center of this biological mystery sits the central hub, the brain located within the mantle, tucked just above the esophagus. If you were to look at a cross-section of an octopus, you wouldn't see a single, unified mass like a human brain. Instead, you would see a complex, ring-shaped structure, a sophisticated knot of neural tissue that acts less like a dictator and more like a high-level executive overseeing a massive, distributed corporation. This central hub is the seat of the octopus's most complex cognitive functions. It is here that the animal processes high-level sensory data, manages long-term memory, and makes the big-picture decisions. Where is the shelter? Is that shadow a predator or a meal? How do I navigate this specific reef? It is the hub of intentionality, the place where instinct meets strategy. However, to call it the brain is almost a misnomer. While the central hub manages the why of an action, it has largely abdicated the how. In a human, if you decide to reach for a cup, your motor cortex sends a precise, step-by-step sequence of electrical impulses down your spinal cord to your arm. Your arm is essentially an effector of your will. In the octopus, this process is radically different. The central hub provides the broad directive, move toward that object, but the granular, mechanical details of the movement are handled elsewhere. The central brain is surprisingly small relative to the sheer volume of neurons distributed throughout the body. In fact, a staggering 2/3 of an octopus's total neuronal count resides not in the head, but in the arms. This creates a fascinating tension. The central hub must act as a conductor of an orchestra where every musician is capable of composing their own music. This leads us to a startling realization about the nature of their consciousness. The central hub is not managing a collection of simple reflexes. It is coordinating a network of semi-autonomous intelligences. When the central brain sends a signal to an arm, it isn't providing a map, it is providing a suggestion. The arm receives the intent, but it uses its own local neural processing to calculate the texture of the sand, the resistance of a crevice, and the exact tension required to grip a shell. This architectural split creates a unique cognitive phenomenon. The central hub allows for a unified sense of self, a way for the octopus to navigate the world as a single entity, while the peripheral nervous system allows for a level of multitasking that defies vertebrate logic. It is a system designed for a world of infinite variables, where a single command center would be too slow, too rigid, to respond to the chaotic, multisensory onslaught of the ocean floor. The central hub is the eye of the storm, a calm, calculating center of high-order thought, surrounded by a whirlwind of independent, thinking limbs. To understand the octopus, we must understand this delicate balance, the marriage between the singular will of the head and the distributed brilliance of the body. Imagine, for a moment, a body where your hands could hold a conversation with each other without you ever saying a word. If you were to detach a single arm from an octopus, it would not simply go limp. It would not die in the way a human limb would. Instead, for a period of time, that arm would continue to behave with a ghostly, haunting purpose. It would reach, it would grasp, it would taste, and it would react to the world around it, driven by a localized intelligence that exists entirely independent of the head. This is not science fiction. It is the biological reality of the cephalopod. While the central hub manages the macro decisions, the arms are the masters of the micro. Each of the 8 limbs is a self-contained processing unit packed with millions of neurons that function as a localized brain. In a human, the nervous system is a hierarchy. In an octopus, it is a democracy. This decentralized architecture allows for a level of parallel processing that is virtually unparalleled in the animal kingdom. While the central brain is busy calculating a long-term escape route or deciding which direction to migrate, the arms are simultaneously performing a dozen different complex tasks. One arm might be delicately probing a crevice for a hidden crab, while another is testing the texture of a rock to see if it's suitable for camouflage, and a third is independently adjusting its grip on a slippery stone. These limbs do not wait for permission from the head to act. They possess their own sensory motor loops. This means the arm can perceive and act in a closed circuit. When a sucker touches a surface, the sensory input doesn't have to travel all the way to the central brain to be processed. The local neurons in the arm analyze the chemical signature and the physical resistance instantly, triggering a motor response in milliseconds. The arm knows what it is touching before the brain even realizes the arm has moved. But the brilliance of these limbs goes deeper than mere reflex. There is evidence suggesting that these arms possess a form of subconscious memory. They can learn specific patterns of movement and tactile responses through trial and error, refining their dexterity through experience without the central brain ever needing to intervene. They are, in essence, 8 highly specialized autonomous explorers tethered to a single consciousness. This brings us to a profound neurological distinction, the difference between reflex and agency. A reflex is a hardwired, involuntary response, like pulling your hand away from a hot stove. But the octopus arm exhibits something much closer to agency. It can make choices based on local environmental data. It can decide to explore a specific texture or to retreat from a certain sensation, all while the octopus's central mind is focused elsewhere. This creates a biological phenomenon we might call distributed cognition. It challenges our very definition of an individual. If the majority of an octopus's thinking happens in its periphery, where does the self actually reside? Is the octopus a single entity, or is it a collective of 8 intelligent explorers, bound together by a central command? As we move deeper into the anatomy of this creature, we realize that the octopus does not just inhabit its body. It inhabits a network of minds, a swirling, multi-layered intelligence where the boundary between the brain and the limb begins to blur into something entirely new. To truly grasp the scale of this decentralization, we have to look closer at the sheer density of the hardware involved. In a human being, nearly all our cognitive heavy lifting is centralized within the skull. Our limbs are essentially high-end peripherals, sophisticated tools that wait for instructions from the CPU. But in the octopus, the ratio is radically inverted. Roughly 2/3 of an octopus's total neuronal count resides not in the brain, but in the arms. This is not just a matter of more wiring. It is a matter of a fundamentally different computational logic. When we speak of thinking in a human sense, we often imply a singular, linear stream of consciousness. But the octopus operates via a massive, biological parallel processing system. Imagine trying to play a complex game of chess while simultaneously solving a calculus equation and composing a symphony, and doing all of them at once with equal proficiency. This is the daily reality of an octopus. The complexity of this peripheral intelligence is best understood through the specialized anatomy of the suckers. Each individual sucker is a sensory powerhouse, embedded with a sophisticated array of chemoreceptors and mechanoreceptors. This allows the arm to taste and feel with a granular precision that borders on the molecular. Because these suckers are integrated directly into the arm's local neural network, the arm can perform what scientists call tactile discrimination without any input from the central brain. It can distinguish between the smooth surface of a glass jar and the rough texture of a shell, and it can decide autonomously whether to grasp or to recoil. But there is an even more startling layer to this autonomy, the concept of motor programs. Research has shown that octopus arms possess their own internal libraries of movement. When an arm encounters a new obstacle, it doesn't need a blueprint sent from the head to navigate it. Instead, the arm accesses a local software of muscular patterns, testing different curvatures, tensions, and grips until it finds the one that works. It is a localized, trial-and-error learning process. This means that an octopus can learn to navigate a complex, three-dimensional maze using its limbs to feel their way through, even if the central brain is preoccupied with a different stimulus. This brings us to a biological phenomenon that challenges the very foundation of neuroscience, the idea of embodied cognition. In most animals, the brain is the driver and the body is the vehicle. In the octopus, the body is the computer. The intelligence is not just in the arms, it is of the arms. The distinction between thinking and doing begins to dissolve. This decentralized intelligence is not without its biological costs or strange quirks. Because the arms possess such high levels of autonomy, they can sometimes act in ways that seem contradictory to the central organism's immediate goals, driven by local sensory impulses that the central brain hasn't yet synthesized. It is a delicate, constant negotiation between the will of the head and the desires of the limbs. As we peel back the layers of this neurological marvel, we find that the octopus is not just a creature with many limbs. It is a living, breathing, distributed network, a biological masterpiece of multitasking that forces us to ask, if intelligence can be spread across a body, how much of our own mind are we perhaps missing? But if the neurons are the hardware of this distributed network, then we must ask, what is the software that allows these disparate parts to communicate? To understand how a creature with a fragmented brain maintains a cohesive sense of self, we have to look beyond the electrical impulses and descend into the microscopic world of chemical intelligence. In the human brain, we are accustomed to the idea of a centralized chemical command center. We think of neurotransmitters like dopamine or serotonin as signals that travel through a singular, well-defined highway to dictate mood, movement, and thought. But for the octopus, communication is not just a top-down command. It is a complex, multidirectional chemical dialogue. Because the octopus nervous system is so vast and spread out, relying solely on electrical signals, which can be slow or subject to interference, would be inefficient. Instead, the octopus utilizes an incredibly sophisticated array of neuromodulators to bridge the gap between the central brain and the autonomous arms. These are chemicals that don't just trigger a single action, but rather tune the sensitivity of entire neural circuits. Imagine a radio being tuned to a specific frequency. A neurotransmitter might act as the signal, but a neuromodulator acts as the dial, changing how much importance an arm gives to a specific sensation. This allows for a level of local plasticity that is almost unheard of in the animal kingdom. An arm can chemically reconfigure its own responsiveness. If an arm is navigating a high-risk environment, chemical shifts can heighten its tactile sensitivity, making it hyperaware of even the slightest vibration, effectively upgrading its local processing power on the fly without waiting for an order from the head. Perhaps even more fascinating is the role of the octopus's endocrine system, the hormonal messengers that travel through its blood. In most vertebrates, hormones like adrenaline or cortisol provide a global response to stress, affecting the whole body simultaneously. In the octopus, we see evidence of a much more nuanced, localized hormonal control. They possess a unique ability to use chemical signaling to manage the negotiation between the brain and the limbs. This leads us to a profound scientific realization. The octopus utilizes chemical computation. By modulating the concentration of specific ions and neurotransmitters across its distributed network, the octopus can solve problems through chemical gradients. It isn't just sending a yes or no signal. It is creating a shifting landscape of chemical information that allows the body to reach a consensus. This chemical sophistication is also deeply tied to their legendary camouflage. The rapid-fire changes in skin color and texture aren't just driven by nerves. They are facilitated by a complex interplay of neurochemicals that regulate the muscles around their chromatophores. It is a chemical ballet where the distinction between a thought, a feeling, and a physical transformation becomes nearly impossible to draw. As we move deeper into their biology, we realize that the octopus doesn't just use chemistry to function. It thinks with chemistry. Their intelligence is not a singular electrical spark, but a swirling, oceanic tide of molecular information. They are a creature of liquid logic, proving that if you want to build a mind that can master the chaos of the sea, you cannot rely on wires alone. You must master the very essence of the chemical world. But if the octopus thinks with a liquid logic of chemicals, we must ask, how does this intelligence actually perceive the world? For us, the world is filtered through a narrow window of 5 senses, centralized in a skull. For the octopus, the world doesn't just come to them. The world is felt, tasted, and seen through the very surface of their being. To understand the octopus, you must first discard the idea of touch as a mere sensation of contact. In the cephalopod world, the skin is not a boundary. It is a sophisticated sensory organ that blurs the line between perception and action. Every millimeter of an octopus's skin is a high-resolution data port. While we rely on specialized organs like the eyes or the tongue, the octopus possesses a sensory web that covers its entire body. This is driven by a dense concentration of mechanoreceptors, sensors that detect minute changes in pressure and vibration. But it goes far beyond simple touch. Through a process known as tactile vision, the octopus can interpret the texture, hardness, and even the microscopic geometry of an object simply by brushing against it. They don't just feel a rock, they see its shape through the language of pressure. The true miracle, however, lies within the suckers. Each sucker is a masterpiece of biological engineering, housing a localized cluster of neurons that function almost like miniature brains. But these suckers are not just tactile, they are chemosensory. They are equipped with specialized cells capable of tasting the water and the objects they touch. When an octopus reaches into a crevice, its suckers are performing a complex chemical analysis. They are detecting dissolved molecules, amino acids and proteins, that signal whether a morsel is a delicious crab or a toxic sponge. This is gustatory touch. It is a dual-purpose input where the sensation of texture and the flavor of the prey are processed simultaneously in the same neural circuit. This allows the octopus to make split-second decisions. An arm can decide to grab or to recoil based on a chemical flavor profile before the central brain has even fully processed the visual image. Even more startling is the octopus's ability to see with its skin through light-sensitive proteins called opsins. While we traditionally think of opsins as being exclusive to the eyes, research suggests that cephalopods may possess these light-sensitive molecules distributed throughout their skin. This implies a radical possibility, a form of distributed photoreception. It suggests that an octopus might sense light intensity and perhaps even color across its entire body, allowing it to coordinate its legendary camouflage with a precision that feels less like a reflex and more like a conscious, full-body awareness of its environment. This creates a sensory reality that is fundamentally alien to the human experience. We live in a world of discrete inputs, a sound here, a sight there, a taste in the mouth. The octopus lives in a world of continuous, immersive data. They are perpetually bathed in a constant stream of chemical and mechanical information, a 360-degree sensory immersion where the distinction between me and the environment begins to dissolve. They do not merely inhabit the ocean. They feel the ocean's very chemistry as an extension of their own consciousness. If the octopus experiences the world as a continuous, immersive stream of data, then we must confront a question that challenges the very foundation of neurobiology. Where does that data go? In a human, information travels a predictable highway toward a single, central command center. But in the octopus, the highway doesn't lead to a destination. It is the destination itself. To understand the wiring of this genius, we have to stop thinking of the brain as a pilot sitting in a cockpit, controlling a machine. Instead, imagine a symphony where every instrument is capable of composing its own movement. While the octopus possesses a central brain, a ring of neural tissue surrounding the esophagus, this hub is surprisingly small in proportion to its total nervous system. In fact, only about 1/3 of an octopus's neurons are located in this central cluster. The remaining 2/3 are scattered, embedded deep within the muscles of the 8 arms. This is the essence of distributed intelligence. This architectural choice creates a biological phenomenon that defies our traditional understanding of motor control. In a vertebrate, if you want to move your hand, your brain must calculate the trajectory, the muscle tension, and the grip strength, then send the command down the spinal cord. The octopus bypasses this bottleneck. Because the vast majority of its neurons are peripheral, the arms possess a high degree of local autonomy. An octopus arm can explore a complex reef, navigate tight crevices, and manipulate a stubborn shellfish entirely on its own, without the central brain ever needing to issue a specific order. The central brain provides the what, the high-level goal, such as find food or hide from that predator, but the arms decide the how. They are sentient limbs, capable of independent learning, memory, and even rudimentary problem-solving. If an arm is severed, it does not simply go limp. It continues to reach, to curl, and to react to stimuli, driven by a localized neural blueprint that persists even when disconnected from the whole. This decentralization isn't just a curiosity, it is a massive computational advantage. By offloading the grunt work of movement and sensory processing to the limbs, the central brain is freed from the crushing weight of micromanagement. It is liberated to focus on higher-order cognition, strategy, memory, and complex decision-making. It is a masterwork of parallel processing. But this brings us to a profound biological realization. The octopus does not have a body that is controlled by a brain. The octopus is a brain that has been stretched out into a body. Its intelligence is not a localized spark contained within a skull, but a fluid, sprawling network of consciousness that occupies its entire volume. This is a body brain, a biological system where the distinction between thought and movement has been erased. When an octopus changes its color or reaches for a tool, it isn't just executing a command. It is a whole body thought in motion. To study the octopus is to witness a radical alternative to the human way of being. A mind that doesn't just think about the world, but a mind that is physically woven into the very fabric of its own form. If the octopus is a brain that has been stretched into a body, then how does that mind react when it is confined within the rigid, artificial boundaries of a glass box? To a human, a tank is a container. To an octopus, it is a puzzle waiting to be solved. In the world of marine biology and public aquariums, there is a recurring, almost legendary phenomenon: the escape artist. It is a term that carries a sense of whimsy, but for researchers, it represents a profound cognitive challenge. We are not merely seeing an animal acting on instinct. We are witnessing a strategic, calculated attempt to subvert a controlled environment. Consider the sheer physics of the escape. Most animals are defined by their skeletons, the rigid architecture that dictates their limits. But the octopus is a master of the soft body advantage. Because they lack a bony skeleton, their only structural limit is the beak, the hard, parrot-like mouthparts used for feeding. If the beak can fit through a gap, the rest of the octopus can follow. But the genius lies not in the ability to squeeze, but in the ability to find the way out. Observers in controlled settings have documented behaviors that border on the uncanny. An octopus won't just thrash against a glass wall. It will spend hours silently patrolling the perimeter of its enclosure. It uses its distributed nervous system to perform a tactile survey of the environment, feeling for microscopic discrepancies in the seal of a filter pipe or the slight vibration of a loose lid. It is performing a real-time topographical scan, seeking out the one structural weakness in a system designed to hold it. There have been documented cases where octopuses have navigated complex plumbing systems, traveling through dark, narrow pipes to reach an adjacent tank, often to find better food or more interesting neighbors. They have been known to unscrew lids by manipulating the threading with the precision of a locksmith, using the localized intelligence of their arms to apply torque that a central brain might not even be consciously monitoring. Even more startling is the evidence of premeditated escape. In some laboratory settings, octopuses have been observed waiting for a specific event, such as a keeper entering the room or a certain light cycle, to initiate their breakout. This suggests a level of temporal awareness and strategic patience that is rarely seen in the animal kingdom. They aren't just reacting to a stimulus, they are waiting for an opportunity. This behavior forces us to reconsider the concept of containment. When we place a highly intelligent, decentralized mind into a closed system, we aren't just housing an organism, we are creating a cognitive conflict. The octopus views the enclosure not as a home, but as a barrier to its autonomy. Every time an octopus finds a way through a filter, or manipulates a latch, or squeezes through a gap no wider than a coin, it is sending a clear biological message. Intelligence, when distributed and decentralized, is fundamentally difficult to imprison. Their escape artistry is the ultimate expression of their cognitive architecture, a demonstration that a mind woven into the body is a mind that will always find a way to expand its reach. But what happens when the octopus is not trying to leave, but is instead trying to stay? If the escape artist is defined by its desire for autonomy, the architect is defined by its need for security. In the wild, an octopus is a paradox. It is a highly intelligent predator, yet it is also a soft-bodied creature in a world filled with teeth. To survive, it cannot simply hide. It must engineer. This brings us to one of the most sophisticated displays of environmental manipulation in the animal kingdom: the construction of the den. For most marine organisms, a home is something found, a discarded shell, a crevice in a rock, a hollowed-out log. But for the octopus, a home is something made. They do not merely occupy space, they curate it. When an octopus selects a site for its lair, it begins a process of meticulous site preparation. Using the tactile precision of its suckers, it will clear away silt, move pebbles, and rearrange the seabed to create a fortified perimeter. But the true brilliance lies in the outward-facing nature of their architecture. An octopus doesn't just build a fort to hide in, it builds a fort to observe from. They often position the entrance of their den to provide a strategic vantage point, allowing them to monitor the currents for approaching prey or the subtle vibrations of a predator. The most extraordinary evidence of this cognitive engineering is seen in species like Octopus marginatus, the veined octopus. This creature has demonstrated something that was once thought to be the exclusive domain of vertebrates: tool use. Researchers have observed these octopuses collecting discarded coconut shells or large seashells, carrying them across the ocean floor, and assembling them into a portable, armored bunker. This is not a simple, instinctual hiding reflex. The process of transporting these heavy, cumbersome objects requires a sophisticated understanding of physics and spatial reasoning. The octopus must calculate the weight of the shell, the drag of the current, and the most efficient way to maneuver the object using its distributed limbs. They are essentially carrying their house with them, demonstrating a level of foresight, the ability to prepare for a future state of vulnerability. That is a hallmark of high-order intelligence. Furthermore, the architecture of an octopus den is often a masterclass in deception. Some species utilize decoy, entrances, or arrange stones in a way that obscures the true depth of their burrow. They are essentially employing camouflage not just on their skin, but on their very geography. This ability to manipulate the physical world to serve a long-term survival strategy suggests that the octopus mind does not just perceive the environment, it perceives the potential of the environment. They see a shell not just as an object, but as a shield. They see a pile of rocks not just as terrain, but as a wall. By building, by carrying, and by rearranging, the octopus proves that intelligence is not just about solving problems in the moment. It is about the ability to reshape the world to suit one's needs. They are the ocean's silent engineers, turning the chaos of the seafloor into a structured, fortified realm of their own design. But if the coconut shell represents the ultimate mobile fortress, what of the more permanent, more subtle ways they manipulate the world around them? To understand the full scope of cephalopod ingenuity, we must look beyond the heavy lifting of shells and into the delicate, almost surgical application of inanimate objects. In the complex topography of a coral reef, an octopus does not merely interact with the debris of the ocean. It selects, it tests, and it employs. While the veined octopus is the celebrated pioneer of the portable home, other species exhibit a more nuanced form of tool usage, one that borders on the tactical. There are documented instances of octopuses utilizing specific stones not as walls, but as tools for manipulation or as defensive barricades. Consider the way an octopus might use a single, heavy stone to plug a narrow crevice, creating a customized valve that can be opened or closed at will. This isn't just blocking a hole, it is the creation of a controlled environment. By manipulating these objects, they are essentially creating a technological barrier that can be adjusted based on the immediate threat level. What is perhaps even more startling is the evidence of object selection. In controlled studies, octopuses have shown a preference for objects that serve a specific functional purpose. They don't just grab anything that drifts by. They demonstrate a capacity to distinguish between a useless piece of kelp and a structurally sound piece of discarded masonry or shell. This ability to evaluate the physical properties of an object, its hardness, its weight, its shape, suggests a mental model of the physical world that is remarkably similar to our own. They are performing a silent, internal physics simulation before they ever make a move. This leads us to a profound realization. The octopus is one of the few invertebrates capable of extending its body through the use of external objects. When an octopus uses a stone or a shell, it is effectively bridging the gap between its soft, vulnerable biology and the hard, unforgiving reality of its environment. It is a form of biological augmentation. Furthermore, we must consider the cognitive cost of this behavior. To use a tool, an animal must possess what psychologists call means-end reasoning. They must understand that action A, picking up the stone, will lead to result B, protection from a predator. This requires a level of temporal awareness, a connection between the present action and a future consequence. That was once thought to be a uniquely human trait. In the deep, quiet reaches of the ocean, these small, calculated movements, the dragging of a shell, the placement of a stone, the curation of a rocky perimeter, are the fingerprints of a sophisticated mind. They are the evidence of a creature that refuses to be a victim of its own anatomy. They do not just live in the ocean, they exploit its mechanics. They turn the ocean's discarded remnants into a toolkit, proving that even in a world of teeth and claws, the most powerful weapon is not a fang or a fin, but the ability to think, to plan, and to use. The octopus is not just surviving the seascape, it is mastering it, one stone at a time. But if the mastery of objects is the octopus's way of shaping its world, how does it use that same intellect to conquer its neighbors? In the predator-prey dance of the reef, most animals rely on a simple script: the fast chase the slow, or the camouflaged strike from the shadows. But the octopus does not follow a script, it writes its own. For this cephalopod, hunting is not a feat of raw athleticism, but a high-stakes game of psychological warfare and tactical deception. To witness an octopus hunt is to witness a masterclass in cognitive redirection. While we often focus on their ability to disappear into the background, the true genius lies in their ability to manipulate the visual perception of their target. This is not merely passive camouflage, it is active, deceptive signaling. Some species have been observed using dynamic mimicry, where they don't just match the color of a rock, but mimic the specific texture and movement of a non-threatening organism, perhaps a swaying sea fan or a harmless jellyfish, to lure curious prey into a fatal proximity. They are not just hiding, they are performing. This brings us to one of the most sophisticated hunting strategies in the invertebrate kingdom: the use of ambush lures. Consider the mimic octopus of Southeast Asia. It doesn't just hide, it transforms. By selectively undulating its arms and altering its skin pattern, it can impersonate a venomous sea snake or a toxic flatfish. This is a calculated gamble. The octopus is performing a biological bluff, using the reputation of another species to clear a path or to frighten competitors away from a food source. It is utilizing the evolutionary fears of other creatures to its own advantage. Yet the deception extends beyond the visual. The octopus employs a form of sensory cloaking. By controlling the movement of its mantle and the expansion of its suckers, it can minimize the hydrodynamic signature it leaves in the water. It moves through the currents with a ghost-like efficiency, effectively silencing its presence in the pressure-sensitive world of the ocean. To a crustacean or a small fish, the octopus isn't just invisible. It is non-existent, until the very moment the trap is sprung. Even more fascinating is the evidence of iterative strategy. Observations suggest that when a preferred hunting method fails, the octopus does not simply repeat the mistake. Instead, it appears to assess the failure and pivot. If a direct approach is detected, it may switch to a wait-and-see tactic, repositioning itself to exploit a different environmental variable, perhaps using a change in light or a shift in current to mask its approach. This ability to switch tactics mid-hunt suggests a level of real-time problem-solving that is incredibly rare. It is the difference between a programmed reflex and a conscious decision. This tactical brilliance reveals a startling truth. The octopus understands the mind of its prey. It recognizes that its target operates on a set of predictable sensory rules, and it systematically breaks them. It exploits the gaps in their vision, the limits of their lateral lines, and the instincts of their fear. In the silent, high-pressure theater of the deep, the octopus is not merely a predator. It is a strategist, a deceiver, and a grandmaster of the hunt, proving that in the struggle for survival, the sharpest edge is often an invisible one. But if the octopus can master the psychology of its prey, how does it master the geography of its home? To a human, a coral reef is a beautiful, chaotic landscape. To an octopus, it is a three-dimensional, high-stakes labyrinth, a dense, shifting matrix of crevices, overhangs, and predatory corridors. Navigating this environment isn't just about moving from point A to point B. It is about maintaining a mental blueprint of a world that is constantly changing. This is the realm of cognitive mapping, and it is here that we see the octopus move beyond mere instinct and into the territory of true spatial intelligence. While many marine creatures rely on simple chemotaxis, following a scent trail, or phototaxis, moving toward or away from light, the octopus employs something far more sophisticated, a complex, internal representation of space. Research suggests that octopuses do not just react to the reef, they know it. They build mental maps that allow them to calculate the most efficient route between their den and a distant foraging ground, often bypassing obstacles that would baffle a less intelligent organism. This spatial awareness is fueled by their unique neural architecture. Because their intelligence is distributed, the map isn't just stored in a single central command center. As an octopus glides through a narrow coral tunnel, its arms are simultaneously processing tactile data, feeling the geometry of the walls, and feeding that information back to the central brain to refine the mental image. It is a real-time, multi-sensory integration of space. They are essentially building a live, 3D topographical model of their surroundings in their mind as they move. Perhaps most stunning is their ability to engage in path integration, a phenomenon also seen in highly intelligent mammals. This is the ability to track one's position based on a continuous internal calculation of movement and direction. Even if an octopus is pushed into darkness or forced to navigate a complex, winding detour by a predator, it can dead reckon its way back to its home den with startling precision. It doesn't need to see a landmark. It knows where it is because it has mathematically accounted for every turn and every meter traveled. But the genius of their mapping goes even deeper than simple navigation. Octopuses demonstrate what scientists call allocentric spatial memory. Most animals use egocentric navigation, mapping the world in relation to their own bodies, e.g., the rock is to my left. However, evidence suggests the octopus can understand the relationship between objects in the environment independent of itself. It understands that the shell is near the crevice, creating a stable web of environmental landmarks. This allows them to perform complex search and rescue style maneuvers, returning to specific, high-value locations even after long periods of absence. This mental architecture also allows for spatial memory optimization. An octopus doesn't just wander aimlessly. It remembers where the high-yield hunting spots are, where the safest hiding places lie, and crucially, where the most dangerous predators frequent. They are not just surviving the reef, they are optimizing their lives within it. In the darkness of the reef, where visibility is often a luxury, the octopus operates with the precision of a seasoned navigator using a digital GPS. They possess a profound, invisible understanding of the architecture of the ocean, proving that to truly conquer an environment, you must first be able to hold its entire shape within the theater of your mind. But what happens when the map fails, or when the octopus encounters a challenge that isn't written in its genetic code? In the wild, intelligence is not merely the ability to remember where a shell lies. It is the ability to navigate the unknown. Most animals are governed by a rigid set of biological instructions. If X happens, do Y. This is instinct, a reliable but inflexible survival mechanism. But the octopus operates on a different plane. It possesses the capacity for true, autonomous learning, the ability to encounter a problem, fail, analyze the cause of that failure, and adjust its strategy accordingly. This is the essence of trial and error, a hallmark of high-level cognition that requires an animal to move beyond what it is doing and begin understanding why it failed. Consider a complex task, such as opening a specialized jar or navigating a multi-stage puzzle box in a laboratory setting. An octopus does not simply repeat the same fruitless motion indefinitely. It doesn't get stuck in a loop of repetitive behavior like a simpler organism might. Instead, it demonstrates a sophisticated process of elimination. It explores, it probes, it pulls, and it twists. When a specific movement fails to yield a reward, the octopus doesn't just try harder, it tries differently. It shifts its tactile approach, perhaps changing the angle of its suckers or the sequence of its arm movements. It is essentially running a series of real-time biological simulations, testing hypotheses against the physical world. This capacity for learning without guidance is what scientists call operant conditioning, achieved through independent discovery. In many species, learning requires a social component, a parent demonstrating a behavior or a predator teaching a juvenile. But the octopus is a solitary creature. It has no elders to consult, no school to follow, and no cultural tradition to inherit. Every breakthrough it achieves is a lonely, private victory. It is a self-taught scholar of the sea. This learning from mistake is even more profound when we look at their neurological plasticity. Every time an octopus fails and succeeds, its neural pathways are being physically reshaped. This is not just temporary memory, it is the structural rewiring of its distributed brain. Research has shown that octopuses can exhibit latent learning, where they acquire information about their environment through trial and error even when there is no immediate reward. They are gathering data, building a library of what works and what doesn't, preparing for future contingencies. There is a fascinating, less discussed aspect to this, the role of frustration and persistence. In controlled studies, when faced with a difficult mechanical task, octopuses don't just exhibit a random distribution of movements. They show a directed, purposeful attempt to solve the problem. They demonstrate a form of cognitive persistence that is startlingly similar to that of primates. They can experience a eureka moment, a sudden shift in strategy that resolves a long-standing obstacle. This ability to learn through error is the bridge between mere reflex and true intellect. It transforms the octopus from a creature that simply reacts to its environment into a creature that actively interrogates it. By turning every mistake into a data point, the octopus does more than just survive. It evolves, in real time, through the sheer power of its own curiosity. If intelligence is the ability to solve problems, then personality is the unique way an individual chooses to face them. When we observe octopuses in a laboratory or a controlled reef environment, we see something that challenges our traditional understanding of animal behavior. In many species, behavior is a predictable spectrum, a set of biological defaults. But with the octopus, we encounter something far more intimate and startling: individuality. No two octopuses, even those of the same species raised in identical conditions, respond to the world in the same way. Some are bold, investigative explorers, rushing toward new objects with a fearless, almost reckless curiosity. Others are cautious, neurotic, and intensely shy, preferring to remain shrouded in shadows, observing the world from a distance before committing to a single movement. This isn't just a difference in temperament. It is a manifestation of their complex, decentralized nervous system. Because their intelligence is distributed across their limbs, their personality is not just a centralized psychological state, but a physical expression of how their entire body interacts with the environment. A bold octopus isn't just mentally courageous. Its entire peripheral nervous system is tuned to a high state of sensory engagement, its arms reaching out with a proactive, exploratory impulse. Researchers have begun to document what we might call behavioral phenotypes in cephalopods. We see individuals that exhibit neophobia, a profound fear of anything new, and others that display a high degree of novelty-seeking. This distinction is critical. It suggests that the octopus possesses a self, a stable internal framework that filters sensory input and dictates emotional response. One of the more obscure and fascinating aspects of this individuality lies in their idiosyncratic problem-solving. In various studies, scientists have noted that when presented with the same complex puzzle, different octopuses will develop entirely different signatures of movement. One might rely on a brute force approach, using its mantle to push against a barrier, while another might employ a delicate, surgical manipulation, using the fine motor control of a single sucker to find a seam. These aren't just different tactics, they are different cognitive styles. They are the creative fingerprints of a non-human mind. This individuality is further complicated by the role of their chromatophores, the pigment cells that allow for instantaneous color change. While we often view color change as a functional tool for camouflage, it is increasingly being viewed as a window into their internal state. An octopus's mood is written on its skin. A frustrated octopus may pulse with dark, aggressive patterns, while a relaxed one might settle into a calm, mottled texture. Because their skin is effectively a secondary brain, their personality is not hidden behind a mask. It is broadcasted to the world. This brings us to a profound realization. If an organism possesses distinct temperaments, varying levels of curiosity, and unique problem-solving styles, we are no longer talking about a biological machine executing a program. We are talking about a sentient being with a character. To study the octopus is not merely to study a species, but to encounter a collection of distinct, solitary souls, each navigating the vast, crushing silence of the ocean with a way of being that is uniquely, stubbornly their own. But if personality is the how of their existence, then play is the why. In the traditional hierarchy of biology, behavior is almost always viewed through the lens of utility. An animal hunts to eat, it hides to survive, it migrates to reproduce. Every action is a calculated transaction with the environment, driven by the cold, hard math of Darwinian necessity. But what happens when an animal does something that serves no purpose? What happens when a creature engages in an activity that offers no calories, provides no protection, and carries no reproductive reward? What happens when an animal plays? To witness play in an octopus is to witness a profound break from the biological script. In laboratory settings, researchers have observed octopuses engaging in what can only be described as object play. They will take a piece of inanimate debris, perhaps a discarded shell or a plastic fragment, and toss it into the water column, watching it drift, only to catch it and toss it again. They manipulate these objects not to consume them, but to interact with them. This is a hallmark of high-level cognition, the ability to decouple an object from its functional utility and treat it instead as a source of sensory stimulation. This behavior hints at something deeper than mere tactile exploration. It suggests the existence of intrinsic motivation. In cephalopods, we see evidence of playful manipulation, where an individual might spend hours spinning a coconut shell or juggling a stone, driven by a cognitive itch that can only be scratched through repetitive, non-essential movement. There is a specific, less discussed phenomenon known as sensory-motor play. Because the octopus's skin is a massive, distributed sensory organ, play may be a way of calibrating their decentralized nervous system. By interacting with novel textures and resistances, they aren't just passing time. They are fine-tuning the incredibly complex communication between their central brain and their 8 independent limbs. It is a form of neurological exercise, a way of sharpening the tools of their genius through sheer, unadulterated whim. Furthermore, the presence of play suggests the presence of boredom, a concept we once thought was the exclusive domain of mammals and birds. If an octopus can experience a lack of stimulation, it implies a mind that requires more than just survival. It requires engagement. It suggests a consciousness that craves complexity. When we see a young octopus darting through a reef, not in pursuit of prey, but in a series of rhythmic, acrobatic loops, we are seeing the expression of a cognitive surplus. They have mastered the basic mechanics of survival so effectively that they have earned the luxury of curiosity. They have moved beyond the what of life, what to eat, where to hide, and have entered the what if. This transition from survival-based instinct to play-based exploration is one of the strongest indicators of true sentience. It suggests that the octopus mind is not just a sophisticated calculator designed to solve the equations of life, but a landscape of experience. It tells us that for the octopus, the ocean is not just a hunting ground or a battlefield. It is a playground. And in that playground, the drive to learn and the desire to wonder are just as powerful as the drive to live. But if play is the expression of that cognitive surplus, then curiosity is the engine that drives it. If play is the luxury of a mind that has mastered its environment, curiosity is the relentless, restless hunger to master the next one. It is the impulse that pulls an organism away from the safety of the known and pushes it toward the edge of the abyss. In most of the animal kingdom, the unknown is something to be feared. It is a source of potential predators, hidden dangers, and wasted energy. But for the octopus, the unknown is a beckoning frontier. This is not merely a reflexive search for food. This is epistemic curiosity, the desire for knowledge itself. We see this in the way an octopus approaches a new object in its habitat. It does not merely glance, it investigates. It uses its suckers to taste the chemical composition of a new rock, its skin to sense the minute pressure waves of a passing shadow, and its eyes to map the geometry of an unfamiliar crevice. They exhibit what biologists call neophilia, an attraction to novelty. While many species exhibit neophobia, or a fear of the new, the octopus often displays a proactive tendency to probe, touch, and manipulate anything that breaks the pattern of its established world. This drive is particularly evident in their sophisticated use of exploratory tactile sampling. Because an octopus possesses a high density of chemoreceptors in its suckers, every touch is an act of profound data collection. When they encounter a strange texture, they aren't just feeling it. They are downloading a complex profile of its density, temperature, and chemical signature. This allows them to build highly accurate internal models of their environment, creating a mental map that is not just spatial, but sensory and multidimensional. There is a fascinating, less studied aspect of this curiosity: its role in cognitive mapping and spatial problem solving. In controlled studies, octopuses have shown an ability to solve complex mazes, not just through trial and error, but through an apparent understanding of the path ahead. They possess a spatial memory that allows them to remember the location of resources and the layout of their territory with uncanny precision. This isn't just instinctual navigation. It is the result of an active, curious mind constantly updating its internal GPS. They are perpetually asking, what lies beyond that coral head? What is the shortcut through this cave? Perhaps most striking is how this curiosity manifests as exploratory risk-taking. We observe octopuses venturing into open, vulnerable waters or entering brightly lit areas to investigate a strange object, momentarily disregarding the fundamental rule of survival: stay hidden. This suggests that the drive to resolve uncertainty, to turn the unknown into the known, can sometimes override the most basic biological imperative of self-preservation. This is the hallmark of a true intellect. A machine follows a program, a survivalist follows an instinct, but a genius follows a question. The octopus does not just inhabit the ocean, it interrogates it. It treats the seabed not as a static backdrop, but as a massive, unfolding puzzle waiting to be solved. In the quiet depths of the reef, curiosity is the spark that transforms a biological entity into a sentient explorer, turning the dark, crushing weight of the deep into a vast, endless library of secrets waiting to be read. But what happens to a mind that is constantly asking questions when there is no one else to share the answers with? In the human experience, intelligence is a bridge. We use our intellect to build languages, to form complex social hierarchies, and to pass the torch of knowledge from one generation to the next. We are social learners. Our brilliance is amplified by the collective. But for the octopus, the light of consciousness burns in a vacuum. They are the ultimate hermits of the deep. Most cephalopods are strictly solitary, living entire lives in profound, unshakable isolation. While a dolphin or a chimpanzee navigates a world of social cues, alliances, and shared traditions, the octopus operates on a singular frequency. There are no mentors to teach a young octopus the nuances of a new hunting technique. There are no elders to pass down the memory of a seasonal current or the location of a hidden reef. Every single discovery, every breakthrough in problem solving, every mastered tool, every strategic deception must be won alone through the grueling, repetitive process of individual trial and error. This creates a unique biological phenomenon, a siloed intelligence. Because they do not communicate complex ideas to their peers, their brilliance is a closed loop. They possess a high-level cognitive capacity, yet they lack a cultural component. In biology, we call this the absence of social transmission of information. It is a profound evolutionary bottleneck. An octopus might spend weeks perfecting the art of using a coconut shell as a mobile fortress, a feat of engineering that would be passed down through generations in a social species. But in the world of the octopus, that knowledge dies with the individual. This isolation is not merely a lifestyle choice. It is a fundamental part of their neurobiology. Their nervous system is built for autonomy, not for connection. The decentralized nature of their brain, where much of the thinking happens in the limbs, favors a self-contained existence. They do not need a tribe to tell them how to move or how to react. Their very anatomy is a masterpiece of self-reliance. But this self-reliance comes at a psychological cost. There is a haunting quality to observing a highly intelligent creature that exists entirely without a peer. When we see an octopus manipulate a complex object or solve a puzzle, we are witnessing a private internal monologue. We are seeing a mind that is capable of profound abstraction, yet has no way to broadcast its findings. They are geniuses living in a world of silence. In some species, we see fleeting moments of interaction, perhaps a brief encounter during mating or a competitive standoff over a den, but these are transactional, not relational. There is no evidence of the cooperative intelligence that defines most of Earth's most successful animals. The octopus does not seek out others to expand its world. It seeks to expand its world through the sheer force of its own curiosity. They are architects of their own solitude. They build dens, they map territories, and they solve the riddles of the ocean, all within the confines of a singular, lonely perspective. They are the ocean's great thinkers, but they are thinkers without a classroom, explorers without a crew, and geniuses who must carry the entire weight of their curiosity entirely on their own. Yet, even in this profound silence, the octopus is never truly mute. If they lack the vocal cords of a whale or the hand gestures of a primate, they possess something arguably more sophisticated: a skin that functions as a living, breathing canvas of the mind. To understand the octopus, you must stop looking at their color as mere camouflage. While their ability to mimic a jagged rock or a patch of sand is a feat of optical engineering, there is a secondary, much more intimate layer to this transformation. Beneath the surface lies a complex biological orchestra of chromatophores, iridophores, and leucophores. These are not just pigments, they are neuromuscular organs. Each tiny sac of pigment is controlled directly by the nervous system, allowing the octopus to change its appearance with a speed and nuance that defies traditional biological limits. But here is the secret. These changes are often not driven by the need to hide, but by the need to feel. When we observe an octopus in a controlled environment, we see the emergence of what researchers call chromatic signaling. This is the visual manifestation of an internal state. When an octopus is startled or perceives a threat, it doesn't just change color to blend in. It undergoes a sudden, violent shift in pattern. You might see a sudden eruption of dark, high-contrast spots, a visual scream of fear or aggression. Conversely, a calm or contented octopus may display soft, rhythmic pulses of pale color, a chromatic sigh. This is a language of light and texture. They can manipulate the reflectance of their skin, using iridophores to create shimmering, iridescent blues and greens that signal physiological arousal. They can alter the texture of their skin, using papillae to turn their smooth surface into something spiked and menacing. It is a high-bandwidth communication system that bypasses the need for sound entirely. Scientific observations have even suggested that these color shifts are linked to a complex emotional spectrum. We see flashing patterns during courtship that act as a visual courtship dance, a way to signal reproductive readiness and individual identity in a world where you cannot call out a name. We see blanching, a sudden loss of color that indicates profound stress or submission. Perhaps most fascinating is the discovery that these color changes are often involuntary. Just as a human's face might flush with embarrassment or pale with terror, the octopus's skin can betray its true intentions, even when the animal is attempting to remain camouflaged. Their skin is a leak in their privacy. It is a window into a nervous system that is constantly reacting, constantly feeling, and constantly broadcasting its internal world to a silent ocean. This brings us to a staggering realization. If an octopus can project its emotions onto its very skin, changing its entire physical identity to reflect its inner state, then the boundary between the self and the environment begins to blur. Their body is not just a vessel for their mind, it is the medium through which their mind speaks. They do not just live in the ocean, they paint their experiences upon it. They are communicating, not through words, but through the very fabric of their being. A silent, kaleidoscopic poetry that tells the story of a genius trying to make itself known in a world of shadows. But if their skin is a canvas of expression, we must ask the question that haunts the borders of marine biology. Is there a someone behind the colors? Are these chromatic shifts merely reflexive, mechanical responses to stimuli, or are they the outward ripples of a genuine internal life? To answer this, we have to move beyond the mechanics of neurology and enter the murky, often controversial waters of sentience. In humans, we define emotion through a cocktail of neurochemicals and subjective experience. For the octopus, the evidence is harder to pin down, yet increasingly impossible to ignore. Consider fear. In a laboratory setting, when an octopus is presented with a predator or a sudden, threatening stimulus, the reaction is more than just a tactical retreat. We see a systemic physiological cascade. Their heart rates spike, their mantle pulses with frantic rhythm, and their skin erupts in the high contrast, warning patterns we discussed. But it goes deeper. Researchers have noted a form of learned avoidance. An octopus doesn't just run from a threat, it remembers the quality of that threat. It exhibits a cautiousness that suggests a lingering, psychological residue of the encounter. They don't just react to danger, they seem to dread it. And then there is the enigma of boredom. In the sterile, predictable environments of many aquaria, scientists have observed something startling: the aimless octopus. When an animal with such a massive, hungry brain is denied any novelty, it doesn't just sit idle. It engages in repetitive, seemingly purposeless behaviors, pacing, rearranging substrate, or even testing the glass with a sense of restless agitation. This isn't just a lack of stimulus. It looks like a cognitive itch that cannot be scratched. It is the hallmark of a mind that requires engagement to remain stable. If an octopus can be bored, it implies a capacity for expectation, a mental state where the present moment is judged against a desire for something more. Perhaps the most profound evidence lies in the subtle traces of satisfaction. We see it in the way an octopus might manipulate a particularly difficult puzzle or successfully navigate a complex labyrinth. There is a momentary pause, a settling of the skin into a rhythmic, soothing pattern, and a purposeful relaxation of the limbs. It is a reward state. In neurobiology, we call this dopamine-driven reinforcement. If an octopus experiences the rush of a successful hunt or the relief of a solved problem, we are witnessing the biological architecture of joy. But this leads us to a profound philosophical discomfort. If we acknowledge that an octopus can feel fear, boredom, or satisfaction, we are no longer looking at a biological machine. We are looking at a subject. We are admitting that there is a private, internal world, a theater of the mind, that exists entirely independent of our understanding. To grant an octopus an emotional life is to accept that intelligence is not a human monopoly, and that empathy is not a mammalian privilege. It forces us to confront the possibility that the ocean is not just a collection of organisms, but a vast, swirling network of feeling, where silent, kaleidoscopic geniuses are experiencing the highs and lows of existence, just as we do, in a language we are only beginning to decipher. But what is the cost of such a vivid internal life? In the grand theater of evolution, intelligence is rarely a free gift. It is a high-stakes investment, and for the octopus, the bill comes due far too soon. We are faced with a biological paradox that defies the conventional logic of survival. In almost every other branch of the tree of life, high cognitive function is paired with longevity. From the complex social structures of elephants to the strategic problem-solving of primates, intelligence is an evolutionary strategy designed to build upon itself, to survive longer, to learn more, and to pass that accumulated wisdom down through generations. But the octopus has taken a different, much more frantic path. They possess a mind capable of profound complexity, yet they are trapped in a life cycle that is brutally, almost cruelly, brief. For many species, life is a marathon of gradual accumulation. For the octopus, it is a sprint toward an inevitable cliff. This is the tragedy of semelparity, a biological phenomenon where an organism puts all its evolutionary energy into a single, terminal reproductive event. Unlike humans, who invest in long-term rearing and social learning, the octopus is hardwired for a one-and-done existence. Once they reach maturity, a biological countdown begins. In many species, the drive to reproduce triggers a systemic physiological decline. They stop eating. Their bodies begin to undergo a process of programmed senescence, where the very systems that allowed them to thrive, their metabolism, their nervous system, their muscular coordination, begin to unravel. This leads us to one of the most heartbreaking mysteries in cephalopod biology, the total loss of knowledge. In the human experience, intelligence is cumulative. We build civilizations because we can teach our children what we have learned. We bridge the gap between generations through language and culture. But the octopus is a solitary genius born into a vacuum. They possess no elders to guide them, no schools to instruct them, and no way to leave a legacy of wisdom. Every single octopus must learn the world from scratch. Every trick, every escape route, every hunting strategy must be discovered through individual trial and error, only to vanish the moment the animal dies. When an octopus dies, its entire universe, every memory of a successful hunt, every lesson learned from a predator, every nuance of its environment evaporates. It is a cognitive dead end. We are witnessing a brilliant, flickering flame that burns incredibly bright, but lacks the fuel to sustain itself. This raises a haunting question for evolutionary biologists. Why? Why would natural selection favor such an immense cognitive investment if it is destined to be wiped clean every few years? Does the cost of maintaining such a massive, energy-hungry nervous system necessitate a shorter lifespan? Or is there something more profound at play? A biological trade-off where the intensity of the experience is prioritized over the duration of the existence? We are left staring at a masterpiece that is written in disappearing ink. The octopus is a testament to the fact that brilliance does not require eternity, but it does demand a certain kind of courage. The courage to learn, to feel, and to master a world that you know you will never truly have time to conquer. To understand this tragedy, we must look closer at the metabolic machinery driving this frantic existence. In the world of biology, there is a concept known as the expensive tissue hypothesis. It suggests that brain tissue is one of the most metabolically demanding substances in existence. A brain does not just process information. It consumes an astronomical amount of ATP, the universal energy currency of life. For the octopus, maintaining a decentralized nervous system, where 2/3 of its neurons reside in its arms rather than its head, is a physiological feat of staggering proportions. They are essentially running a high-performance supercomputer that is wired into every limb, every sucker, and every millimeter of skin. This constant, high-octane neural firing requires a relentless intake of nutrients and a lightning-fast metabolic rate. But here is the hidden catch. The more energy you divert to the brain, the less you have for cellular repair. In most long-lived species, organisms have evolved robust mechanisms for DNA repair and antioxidant defense to combat the oxidative stress that accumulates as we age. But in the octopus, we see a different strategy. Their metabolic engine is tuned for extreme performance, not long-term maintenance. It is as if evolution has optimized them for a high-speed racing engine rather than a reliable family sedan. They are built for the immediate, the intense, and the tactical. They possess a level of sensory processing that allows them to see with their skin and think with their limbs. But this level of complexity creates a biological debt that must be paid in time. There is also a darker biochemical side to this cost. Recent studies into cephalopod senescence suggest that the hormonal cascade triggered by reproduction is not just a signal to mate. It is a systemic shutdown. In many species, the release of specific hormones, often linked to the drive to protect eggs, acts like a biological kill switch. This process, known as programmed cell death or apoptosis, begins to dismantle the very nervous system that made the octopus a genius in the first place. The neurons that once navigated complex mazes and solved intricate puzzles begin to degrade, effectively unraveling the mind before the body even stops functioning. This leads us to a radical possibility that challenges our understanding of evolutionary success. Perhaps the octopus is not an evolutionary mistake or a failed attempt at longevity. Perhaps, instead, they represent a different philosophy of life entirely. In our human worldview, we measure success by continuity, by how much we can build, how long we can live, and how much we can pass on. We view a short life as a failure of survival. But what if the octopus is a biological experiment in intensity over duration? What if evolution has determined that the ability to solve a problem, to master a complex environment, and to experience a high-fidelity sensory reality is more valuable than the ability to repeat those experiences over decades? We are forced to wonder if the octopus is the ultimate expression of a live fast, die young evolutionary strategy. They are the sprinters of the sentient world, possessing a cognitive depth that rivals our own, yet operating on a clock that is ticking towards zero from the moment they hatch. They are a brilliant, fleeting flash of lightning in the dark expanse of the ocean, dazzling, complex, and gone before the thunder can even roll. But what if this flash of lightning is more than just a metabolic accident? What if it is a calculated, albeit devastating, biological gamble? To understand the true weight of this tragedy, we must confront the concept of semelparity. In the lexicon of evolutionary biology, semelparity refers to a Big Bang reproductive strategy, a life cycle defined by a single, massive investment in a solitary reproductive event, followed by certain death. While many animals are itroporous, meaning they can breed multiple times throughout a long life, the octopus is biologically tethered to a singular, terminal crescendo. They do not merely reproduce. They pour their entire existence into a final, desperate act of legacy. For the female octopus, the transition from master strategist to a living vessel for the next generation is a one-way street. Once she begins the process of brooding her eggs, a physiological transformation occurs that is as profound as it is cruel. She enters a state of voluntary senescence. Driven by a relentless hormonal surge, she ceases to feed. The genius that once navigated the reef, the mind that once manipulated tools and outsmarted predators, begins to starve itself to death. She stays with her clutch, guarding them against every threat, cleaning them with her arms, and oxygenating them with a constant flow of water. But as she performs this final act of maternal devotion, her body is undergoing a systemic collapse. Her digestive tract begins to atrophy. Her muscles, once capable of such fluid, superhuman grace, begin to waste away. This is not a gradual decline. It is a programmed biological surrender. In the world of evolutionary mathematics, this is known as the cost of reproduction. For the octopus, the cost is everything. But the tragedy of semelparity extends far beyond the physical death of the individual. It creates what scientists call a knowledge vacuum. In almost every other highly intelligent species, from primates to cetaceans, intelligence is not just an individual trait, it is a cultural one. We learn from our elders. We observe, we mimic, and we inherit a library of survival tactics passed down through generations. We build upon the wisdom of those who came before us. The octopus, however, is a solitary genius born into a world of silence. Because they die shortly after their offspring hatch, there is no opportunity for mentorship. There is no octopus culture. A young octopus enters the ocean with a brilliant, complex nervous system, but it possesses zero ancestral wisdom. It must learn every lesson, solve every puzzle, and survive every predator through raw, unassisted trial and error. Every breakthrough an octopus makes, every clever trick it discovers, dies with it. Their brilliance is a closed loop. It is a brilliant, flickering candle that lights up a room, only to be snuffed out before it can ever be used to light another. This is the fundamental paradox of the cephalopod. They have evolved the most sophisticated hardware the ocean has ever seen, but they have been denied the software of collective memory. They are masters of a world they can never truly teach their children to inhabit. Imagine a library of infinite knowledge, containing the blueprints for survival, the maps of the deep, and the secrets of the reef, only to watch the building burn to the ground the moment a new reader arrives. This is the existential crisis of the cephalopod. To understand why this happens, we have to look deeper than the mere death of the parent. We have to look at the radical isolation of their neurobiology. In the mammalian world, intelligence is a relay race. A mother orangutan teaches her infant which fruits are toxic. A whale calf learns the complex songs of its pod. A human child inherits the language of their ancestors. This is the social transmission of information, the engine of cumulative culture that allows a species to advance without waiting for slow, agonizing genetic mutations. But the octopus is a biological island. Because of their semilporous life cycle, the umbilical cord of knowledge is severed before it can even be tied. When the eggs finally hatch, the parent is often nothing more than a decaying husk, a ghost in the current. The hatchlings emerge into a vast, predatory wilderness, possessing all the processing power of a supercomputer, but with an empty hard drive. They possess the capacity to learn, but they lack the data. This creates a staggering evolutionary inefficiency. Every single octopus, regardless of how clever its predecessor was, must start from zero. If one octopus discovers a revolutionary way to crack a specific type of mollusk shell, that technology does not spread. It does not become a tradition. It does not become part of the species' repertoire. It remains a singular, lonely epiphany that vanishes into the abyss. Even more haunting is the lack of social scaffolding. In many intelligent species, the presence of an elder provides a safety net that allows for exploratory play, the ability to experiment with the environment without immediate fatal consequences. But for a juvenile octopus, there is no safety net. There is no elder to signal that a certain shadow is a predator or that a certain crevice is a trap. They are forced into a brutal, high-stakes apprenticeship where the only teacher is death. This lack of cultural inheritance means that the octopus is trapped in a state of perpetual reinvention. They are masters of the now, but they are strangers to the before. They cannot build upon the successes of their lineage. They can only repeat them through sheer, exhausting individual effort. Biologically, this suggests a profound disconnect in their evolutionary trajectory. While most complex life forms have evolved to favor the group mind, the collective intelligence of a tribe or a pod, the octopus has doubled down on the individual mind. They have achieved a pinnacle of cognitive autonomy that is almost unparalleled in the animal kingdom, yet they pay for this independence with a devastating tax: the inability to belong to a history. They are the ocean's greatest geniuses, but they are geniuses without a legacy. They live, they learn, and they solve the mysteries of the deep, only to leave behind nothing but a void where their wisdom should have been. They are brilliant sparks in a dark ocean, destined to shine brightly, alone, and then disappear forever. How do you measure the value of a mind that leaves no shadow? In the human experience, we define greatness by what we leave behind: our art, our books, our children, our discoveries. We build upon the shoulders of giants, creating a ladder of knowledge that climbs toward the stars. But for the octopus, the ladder is broken at every single rung. This is the silent tragedy of the cephalopod, a profound cognitive dissonance between the complexity of their neural architecture and the brevity of their existence. We have observed octopuses demonstrate advanced spatial memory, complex tool manipulation, and even a form of personality that suggests a rich, subjective inner life. Yet, all of this, every hard-won lesson, every tactical breakthrough, every moment of cognitive mastery, is biologically programmed to die with the individual. Consider the sheer metabolic cost of this brilliance. Maintaining a decentralized nervous system, where billions of neurons are distributed across 8 independent limbs, requires a staggering amount of energy. It is an expensive biological luxury. In most evolutionary models, such an investment is only sustainable if the intelligence provides a long-term advantage to the lineage. But in the octopus, the return on investment is reset to zero every few years. There is a scientific term for this, a lack of cultural evolution. In the animal kingdom, intelligence is usually a communal asset. When a chimpanzee learns to use a stick to fish for termites, that skill can be observed, mimicked, and eventually taught. This creates a cumulative culture, where the species' intelligence grows exponentially over generations. The octopus, however, is locked in a cycle of individualized intelligence. They possess a high-performance engine, but no way to transmit the driving manual to the next generation. This creates a haunting phenomenon, the rediscovery loop. Every generation of octopuses must independently solve the same fundamental problems of survival. They must relearn how to navigate the reef, how to outsmart the moray eel, and how to exploit the seasonal migrations of prey. They are not inheriting a map. They are constantly being dropped into a dark room and told to draw their own. Even more devastating is the neurological implication of their semelparity, the biological mandate to breed once and then undergo rapid senescence. As the octopus prepares to spawn, its body begins a programmed shutdown. The very hormones that drive the reproductive urge also trigger the degradation of the nervous system. The genius literally begins to unravel as it attempts to pass on its genetic code. The mind that mastered the labyrinth is consumed by the body that created it. We are left to wonder if this is an evolutionary mistake or a deliberate, albeit cruel, design. Perhaps the octopus has traded the wisdom of the many for the agility of the one. By investing everything into the individual rather than the collective, they have achieved a level of cognitive autonomy that makes them perhaps the most alien intelligences on Earth. But as we watch them navigate their complex worlds, we cannot help but feel a sense of profound loss. We are witnessing a series of brilliant, solitary lights flickering in the deep minds capable of profound understanding, destined to be extinguished before they can ever truly say, "I have learned this, and now you can, too." If the octopus is a biological masterpiece, then why is its blueprint so fundamentally flawed? When we look at the evolutionary trajectory of complex life, we see a clear pattern. Intelligence is a survival strategy designed to extend the reach of a species. In mammals, a longer lifespan allows for a longer period of learning, which in turn allows for more successful reproduction and the protection of offspring. Evolution generally favors the long game. So, why does the octopus seem to be running a sprint toward a cliff? To understand this genetic mystery, we have to look at the radical, almost violent, way their DNA is expressed. We often think of evolution as a slow, steady accumulation of traits, but in cephalopods, we see evidence of something much more erratic. Recent genomic sequencing has revealed that octopuses possess an extraordinary number of RNA editing events. Unlike humans, who rely heavily on changing the DNA sequence itself to adapt, the octopus can rewrite its genetic instructions on the fly by editing its RNA. This allows them to adapt to temperature changes or new environments with incredible speed, a biological hot fix for a changing ocean. But this extreme plasticity comes at a devastating price. This high-speed genetic editing may be linked to the phenomenon of rapid senescence. There is a growing hypothesis among marine biologists that the octopus has entered an evolutionary trap. Their intelligence is so metabolically taxing, and their ability to adapt via RNA editing is so intense that it may trigger a systemic biological collapse. It is as if their bodies are running at such a high overclocked frequency that the hardware simply melts. We must also confront the enigma of their reproductive strategy, semelparity. In the evolutionary struggle, there is a tension between survival and reproduction. Most species try to balance the two. The octopus, however, has chosen an extreme. They put every single joule of energy, every ounce of cognitive resource, and every metabolic reserve into a single, terminal event. This isn't just a choice, it's a genetic command. During the final stage of their life, known as the senescence phase, octopuses stop eating entirely. Their bodies begin to digest themselves. Their skin loses its ability to camouflage, their limbs become lethargic, and their once brilliant nervous systems begin to degrade. This is not a slow decline due to age, it is an active, programmed suicide. This leads us to the most haunting question in cephalopod biology. Why hasn't natural selection corrected this? If a shorter lifespan is a disadvantage, why hasn't a mutation for a longer life taken hold? One chilling possibility is that the short-life high-intelligence trade-off is actually a highly optimized state. Perhaps the octopus doesn't need a long life because their rapid RNA editing allows them to evolve within a single lifetime. They aren't waiting for the next generation to adapt, they are adapting now. But this creates a profound biological paradox. They have mastered the art of the instant evolution, yet they remain prisoners of a life cycle that forbids the accumulation of wisdom. They are the ultimate innovators, but they are also the ultimate transients. They are brilliant, flickering sparks in the dark, perfectly adapted for a world that requires constant change, but genetically forbidden from ever building anything that lasts. If we accept that the octopus is a brilliant, flickering spark destined to burn out, we are forced to face a much deeper, more unsettling question. What exactly is the nature of the light it produces? For centuries, our definition of consciousness has been deeply anthropocentric. We have operated under the assumption that to be aware, one must possess a centralized, hierarchical mind, a single eye sitting behind the eyes, directing a body like a captain commanding a ship. We equate consciousness with a unified stream of thought, a singular perspective governed by a central processing unit. But the octopus shatters this monopoly. When we observe a cephalopod, we aren't seeing a single mind, we are witnessing a collective. Because 2/3 of an octopus's neurons are located in its arms, the very concept of a unified self begins to dissolve. Imagine if your hands could dream, or if your fingers could make independent decisions about what they wanted to touch without waiting for permission from your brain. In an octopus, the arm is not just a tool, it is a sensory agent with its own local intelligence. It can taste, it can feel, and it can react to the world with a level of autonomy that challenges our most fundamental notions of agency. This brings us to the second intelligence, a form of cognition that is fundamentally non-human. It is a distributed, decentralized consciousness. It suggests that intelligence does not require a throne, it can be a web. This realization forces us to reconsider the hard problem of consciousness. If an organism can exhibit complex problem-solving, emotional expression, and even playful curiosity without a centralized ego, then perhaps consciousness isn't a single thing at all. Perhaps it is a spectrum. We have spent our history looking for a mirror of ourselves in the animal kingdom, but the octopus is not a mirror. It is a window into a different way of being. It challenges the idea that there must be a ghost in the machine. In the octopus, the machine is the consciousness. There is no separation between the processing of data and the experience of the world. When their skin ripples with color to signal fear or excitement, They aren't just showing an emotion, they are becoming the emotion through a direct, neural-to-physical manifestation. Their very biology is a language. This decentralized architecture offers a profound philosophical pivot. If intelligence can be spread across a limb, or a skin cell, or a chemical signal, then our definition of a mind is far too narrow. We have been looking for intelligence in the architecture of the skull, while the octopus has found it in the architecture of the entire body. As we stand on the precipice of understanding this alien mind, we realize that the octopus isn't just a strange animal we are studying. It is a biological proof of concept. It proves that the universe has more than one way to wake up. It proves that sentience does not require a human blueprint. By studying the octopus, we aren't just learning about a creature in the deep. We are learning that the very definition of being alive is far more vast, more fragmented, and more beautiful than we ever dared to imagine. But as we stand mesmerized by this biological miracle, a new, more technical question begins to emerge from the depths. If the octopus has mastered a way of thinking that we are only just beginning to conceptualize, can we translate its organic genius into our own digital language? For decades, the pursuit of artificial intelligence has been a pursuit of the centralized model. We have built our computers, our servers, and our neural networks on the blueprint of the human brain, a massive, singular processor fed by peripheral sensors. We create a brain in a box and try to teach it how to interact with the world. But this architecture has a fundamental flaw. It is a bottleneck. In a centralized system, every piece of data must travel to the core, be processed, and then travel back out. This creates latency, a delay between perception and action that can be fatal in a fast-moving environment. The octopus offers us a way out of this bottleneck through a concept known as edge computing, taken to its ultimate biological extreme. In a cephalopod, intelligence is not a destination. It is a pervasive state. When we look at their neural architecture, we see the blueprint for massively parallel distributed processing. Imagine an AI where the intelligence isn't housed in a single cloud server, but is instead embedded within every single sensor, every single robotic limb, and every single actuator. In this model, the brain doesn't need to decide how to grip a rock. The limb itself perceives the texture, calculates the required pressure, and executes the movement instantaneously. The central hub is relegated to high-level strategy, while the edge, the limbs, handles the granular reality of survival. This is the secret to the octopus's staggering dexterity and speed. They possess what scientists call embodied cognition. Their intelligence is not just in their bodies, it is their bodies. If we can replicate this in silicon, we move away from the fragile, top-heavy AI we have today and toward a swarm intelligence, or soft robotics paradigm. Instead of a single, monolithic supercomputer trying to control a humanoid robot, we could develop a machine composed of thousands of autonomous, interconnected nodes. Each node would possess its own local microintelligence, allowing the system to adapt to damage, navigate unpredictable terrain, and process vast amounts of sensory data in real time without overwhelming a central processor. Furthermore, the octopus teaches us about neuromorphic engineering, designing hardware that mimics the brain's structure. While our current AI relies on the rigid, energy-hungry logic of von Neumann architecture, the octopus operates on a fluid, chemical-electrical hybrid system. They utilize a complex interplay of neurotransmitters that allow for a level of plasticity that our current algorithms struggle to replicate. They don't just follow code, they rewrite their own functional pathways on the fly. As we attempt to build the minds of tomorrow, we are realizing that we have been trying to build gods, singular, all-knowing entities. But the octopus suggests a different path. It suggests that the future of intelligence may not lie in the creation of a single, massive consciousness, but in the orchestration of a billion small, brilliant whispers, working in perfect, decentralized harmony. The octopus isn't just an animal, it is a roadmap for the next evolution of computation. But if the octopus can provide a roadmap for the silicon minds of our future, what does its existence imply about the vast, silent reaches of the cosmos? For centuries, our search for extraterrestrial intelligence has been blinded by a profound form of anthropomorphism. We have been looking for us, for life that breathes oxygen, navigates via light, and processes thought through a centralized, vertebrate nervous system. We scan the stars for signals that mimic our own radio waves, searching for a mirror in the dark. But the octopus serves as a chilling, beautiful reminder that intelligence does not require a human blueprint. It suggests that, when we finally encounter a truly alien mind, it may not be a stranger in a spaceship, but a biological architecture so fundamentally different that we might not even recognize it as thinking at first glance. The octopus is the ultimate proof of concept for convergent evolution gone rogue. It has achieved high-level cognition, complex problem-solving, and sophisticated tool use, yet it did so on a completely separate evolutionary trajectory from us. Our lineages diverged over 500 million years ago. While our ancestors were refining the spinal cord and the skull, the ancestors of the octopus were perfecting a decentralized, soft-bodied mastery of the deep. This tells us that intelligence is not a narrow peak on a single mountain. It is a destination that can be reached via entirely different paths. Consider the radical implications of their biochemistry. While we are carbon-based creatures fueled by copper-free blood, many cephalopods utilize hemocyanin, a copper-based protein, to transport oxygen. This makes their very lifeblood chemically distinct from our own. If we were to find life on an icy moon like Europa or in the subsurface oceans of Enceladus, we shouldn't expect to find brains as we know them. We should be looking for distributed, liquid-based intelligence, systems where thought might be a function of chemical gradients, pressure changes, or even electromagnetic fluctuations in a fluid medium. The octopus challenges our definition of sentience. We often equate consciousness with a self, a singular, I sitting behind the eyes, but an octopus is a collective. With 2/3 of its neurons located in its arms, it exists as a distributed consciousness. If an extraterrestrial intelligence were to emerge from a non-humanoid environment, it might lack a central ego entirely. It could be a swarm, a colonial organism, or a fluidic entity where the concept of an individual is a mathematical impossibility. When we look at the octopus, we are practicing for the first contact. They are a biological rehearsal for the moment we encounter a mind that does not think in sentences, does not perceive through a singular gaze, and does not possess a central command. They teach us that intelligence is a spectrum, not a ladder. To find life among the stars, we must stop looking for beings that think like us and start looking for the octopuses of the universe. The brilliant, alien geniuses that have mastered the art of being fundamentally, beautifully, and terrifyingly different. But as we stand on the precipice of these cosmic realizations, we are forced to confront a devastating irony. We are searching for intelligence among the stars, while simultaneously destroying the most profound intelligence on our own planet. It is a profound tragedy of the modern age that we are only just beginning to decode the language of the cephalopod, yet we are already erasing the ink from their pages. We have spent centuries viewing the ocean as an inexhaustible resource, a vast, empty blue desert, rather than what it truly is, a complex, living library of sentient thought. And right now, that library is burning. The threats facing the octopus are not merely environmental, they are existential. As ocean temperatures rise due to anthropogenic climate change, we are witnessing a silent disruption of the delicate chemical balances these creatures depend on. For a creature that relies on hemocyanin, that copper-based blood we discussed, the metabolic cost of living in warming, less oxygenated water is immense. We are quite literally suffocating the very minds we are trying to understand. Then there is the pervasive shadow of ocean acidification. As the seas absorb excess carbon dioxide, the pH levels drop, altering the very chemistry of the water. For many marine organisms, this is a crisis of calcium, but for the octopus, it is a crisis of cognition. Emerging research suggests that shifting acidity can impair the neural pathways of cephalopods, potentially dulling their legendary problem-solving abilities and disrupting their sensory perception. We are not just changing their habitat, we are potentially altering their ability to think. Beyond the chemistry, there is the direct, physical impact of human industry. Deep-sea mining, a burgeoning frontier driven by our hunger for minerals, threatens to pulverize the complex reef and seafloor architectures that octopuses call home. When we dredge the ocean floor, we aren't just moving silt, we are destroying the intricate architectural blueprints that these geniuses use to build their dens and hide from predators. We are dismantling the stage upon which their intelligence performs. And we cannot overlook the invisible killer: plastic pollution. Microplastics have been found even in the deepest trenches, entering the food web and accumulating in the tissues of cephalopods. We are introducing synthetic, non-biodegradable chaos into a biological system that has spent millions of years perfecting a delicate, chemical harmony. We must ask ourselves, what is the cost of our ignorance? If we allow these distributed minds to vanish before we have even mapped their neural networks, we aren't just losing a species. We are losing a unique way of being. We are burning the only manual we have for understanding non-centralized consciousness. To protect the octopus is to protect a different way of knowing the world. It is an act of humility. It is an admission that our dominance over the earth does not grant us the right to silence its most curious inhabitants. As we look to the heavens for signs of life, let us ensure that we do not let the most extraordinary life we already know slip through our fingers, lost in the dark, silent waters of our own making. What if the key to understanding the future of life on Earth, and perhaps beyond it, lies not in looking up at the stars, but in looking down into the crushing depths of our own oceans? For too long, our scientific paradigm has been built upon a human-centric blueprint, a singular, centralized consciousness housed within a skull, directing a body like a captain commands a ship. But the octopus offers us a radical alternative. It suggests a symbiotic relationship between mind and matter that we are only beginning to grasp. As we move forward into an era of unprecedented technological and ecological change, the study of the cephalopod is no longer just a niche branch of marine biology. It is becoming a fundamental shift in our philosophy of nature itself. This shift begins with the concept of embodied intelligence. In humans, the brain is the master and the body is the servant. In the octopus, the body is part of the brain. Their arms possess a degree of autonomy that challenges our very definition of the self. When we study how an octopus arm can navigate a complex crevice, taste a chemical signal, and exert force, all without a single command from the central ganglia, we are learning about a decentralized way of existing. This has profound implications for the future of robotics and artificial intelligence. We are moving away from the dream of a centralized supercomputer and toward the reality of swarm intelligence and soft robotics, machines that don't just follow instructions, but feel and react through their very structure. But the symbiosis goes deeper than technology. It extends to our relationship with the biosphere. The octopus teaches us that intelligence is not a ladder with humans at the top, but a vast, branching tree of diverse possibilities. By observing them, we are forced to move from an anthropocentric view, where we are the sole arbiters of complexity, to a biocentric view, where we recognize that sentience can emerge in forms that are fundamentally alien to our own experience. This realization fosters a new kind of ecological empathy. If a creature can possess a personality, a sense of play, and a capacity for tactical deception, then the ocean is no longer just a collection of biological resources. It is a community of subjects. To study the octopus is to realize that we are part of a global, interconnected web of minds, many of which operate on principles of chemistry and distributed neural networks that we are only just beginning to decode. As we face the dual challenges of planetary survival and the rise of synthetic intelligence, the octopus stands as a bridge. They are a living testament to the idea that complexity does not require a human template. They show us that intelligence is a flexible, emergent property of life, capable of thriving in the most extreme environments through radical adaptation. Ultimately, the symbiotic future we seek is one where our understanding of biology and our development of technology are no longer at odds, but are informed by the ancient, elegant logic of the cephalopod. By learning to respect and mirror the decentralized, sensory-driven brilliance of these creatures, we may finally learn how to live more harmoniously within the complex living library of our own planet. We are not just studying an animal, we are studying a different way to be alive. What if the greatest mystery in the universe isn't waiting for us in a distant galaxy, but is currently pulsing silently beneath a reef just a few miles from our shores? We have spent centuries searching for intelligence by looking for mirrors of ourselves, creatures that speak, tools that we recognize, and logic that follows a linear path. But the octopus defies the mirror. It is a biological enigma that refuses to be categorized, a creature that has mastered the art of existence through a blueprint that is entirely, beautifully, and terrifyingly alien. As we close this journey, we must confront the unsettling truth. We are still standing on the shoreline of their understanding. We have mapped their genomes, decoded their RNA editing capabilities, a process where they can essentially reprogram their own genetic instructions in real time to adapt to temperature changes, and observed their decentralized neural networks. Yet, the core of their being remains an unsolved riddle. How does a creature with a lifespan so fleeting that it barely scratches the surface of a human decade manage to achieve such profound cognitive depth? There is a haunting dissonance in their biology. A high-speed processor running on a battery that is destined to expire almost as soon as it is fully charged. This ephemeral genius leaves no legacy. They die without passing on the wisdom they spent a lifetime acquiring, making every individual octopus a unique, unrepeatable library of experience that vanishes into the currents the moment it is written. They are the ocean's ultimate outliers. They represent a failed evolutionary experiment if you define success by longevity or social structure, but they represent a triumph of pure, raw adaptability. They prove that intelligence does not require a stable society, a written language, or even a central command center. It only requires the drive to interact with the world. In the coming decades, as we race to build sentient machines and explore the moons of Jupiter, the octopus will likely serve as our most important North Star. They remind us that consciousness is not a human monopoly, but a spectrum of light, and we have only been looking at one narrow frequency. When we finally encounter life among the stars, it may not look like us. It might not have a central brain, it might not communicate with sound, and it might not even be composed of the same rigid structures we take for granted. It might move, think, and feel exactly like the creature drifting through the kelp forests of Earth. The octopus is a reminder that the universe is far more creative than our textbooks allow. It challenges our ego, humbles our science, and expands our imagination. We are left not with answers, but with a profound sense of wonder. We are left realizing that the deep blue is not just a habitat, but a vast, dark laboratory of the mind, a place where genius hides in plain sight, wrapped in shifting colors and 8 graceful arms, waiting for us to finally learn how to truly see. The riddle of the octopus is not just a question of biology. It is a question of what it means to be alive. And as the tide rolls in, we realize the most important lesson of all. The more we learn about them, the less we truly know about ourselves.